All right. Hi, I'm Stone out there. So, we are going to go over some of the atmospheric basics I learned on my fall meteorology course. It has been a little bit since I've reviewed them, so bear with me. So we're going to start with geopotential height, as this will tell you why we even use H5 and what the H5 map is actually representing and why it matters. Next, we'll go over cyclonic flow, as how cyclonic flow actually functions is extremely important when it comes to upper level winds, which is here. And upper level winds drive a lot of divergence. It drives a lot of the lift in the atmosphere, which is also how we get to cyclone formation. We will then also dovetail that with some vorticity, as they are all related, before finishing off with lift and F-gen, which sort of combines all of these and focuses it. So, let us start with geopotential height. Don't know why. Yeah, let's try this. There we go. So, geopotential height is based on the, let me make sure I pronounce it correctly, have my notes pulled up here. It is based on the hyposymmetric equation, which determines atmospheric thickness. Now, I could derive the equation for you, but you don't need to know that. Instead, let's think about it intuitively. We all know that cold air is dense, right? So, if I have a pulsar of air, which just means a specific amount of air, and say it is 0 degrees Celsius, right? These little dots are the air particles, and they're relatively close together, right? So that's how thick that layer of air is. Now, if we take this exact same layer of air, due to the ideal gas law, if we increase its temperature and everything else stays the same, its volume will increase. And in the atmosphere, that means its thickness increases. So at 30 degrees Celsius, that same volume of air is now more spread out. See, the dots are further apart. Now we can visualize the difference in thickness. So that is how atmospheric thickness functions. It is a function of your temperature. Colder means that the air is thicker. Well, sorry, the air is denser, but that also means it takes up less space, so it is in a way thinner vertically. Like it's a thinner vertical slice, is what I mean. While warmer is a thicker horizontal slice. Now, to show how this interacts with height, we're going to use an example of a land-sea boundary. Land-sea buoys. You can think about this next time you're at the ocean. So, that's the beach, that's the water. Let's say it's sunny out, right? The water's cooler, so its column of air looks like this, nice and densely packed. Now, land, sunny out, right? So it's absorbing more heat, and it's warmer, so the air is less dense. So according to our atmospheric thickness we went over, it will occupy a thicker layer in the atmosphere. It will take up more vertical space. Now, what does this cause? Well, at the surface level, we know that if the air is denser, it's high pressure, right? This is just basic fluid dynamics. This is a high pressure area, right? And this is comparatively low density. So we have a surface low. And as we all know, air flows from high density to low density, right? Now, what about in the upper levels? In this case, probably right above the atmospheric boundary layer, so maybe, 900 millibars. Well, at 900 millibars, this is the opposite, right? That's what's really interesting. So, up here, right, if we compare this at this thickness, we'll notice this layer occupies that space, right? So if this is 900 millibars, it's down here. Well, this one is up here, right? So naturally, now this is more dense higher up. Honestly, this took a lot for me to wrap my head around, right? But once you get this, it answers a lot of questions. So this means that this 900 millibars wants to flow into this now less dense. So say this is 800 millibars because of how dense this lower part of the atmosphere is, right? So it is less pressure. Millibars is just a measure of pressure. So this high pressure now flows to this low pressure. What do we see? Well, the air sinks, and then low to high rises. Right? That is more or less, just making sure I got everything right, how this works. Now, I know that this is flowing from low pressure to high pressure, but it's convective. The main thing you want to understand is this, how this is low at the surface, high aloft, low aloft, high at the surface. And in like mesoscale environments, you can get this convective couplet, not couplet, I guess couplet works, which will subsequently result in convection. That's why you have those sea boundaries. They flow inward, and they have that layer of puffy cumulus clouds, and possibly, if they interact with other mesoscale factors, thunderstorms, right? In part, atmospheric thickness can also explain why we form high and why cold air is associated with high pressure, right? It's denser, so it's typically higher pressure. Well, warm air is typically lower pressure at the surface. Yeah, so that's geopotential height. So when you look at a geopotential height map, you're seeing how dense, right, how cold is the air. So if, say, the atmospheric profile is very cold, this 500 MB right here, surface is way down here, right? Well, if this atmospheric profile is warmer, this 500 MB is up here. So there's your height line, right? And if you look from, say, a constant level, say like right here, well, you would say, oh, well, this 500 MB line is actually down at, I don't know, some other number, right? And this one's higher up. So that's how you get those different values when you're looking at the base 500 millibar height map. We will come back to how geopotential height impacts everything else later. I'm gonna stop the video now because I'm using my phone and I don't know how much storage it has. All right, now let's continue with the second part of our lesson, cyclonic flow. And this is all based on the Coriolis effect. That's why it's already drawn out. What does the Coriolis effect state? In the northern hemisphere, it states that winds are deflected to the right. Right? So here's this globe. Hopefully you can see it. And in the mid-latitudes, as we all know, we have winds which are westerlies. Now, why are they westerlies, right? Coriolis effect. So here, let me redraw this. Our winds, right, they start just moving straight north because of the atmospheric circulation cells, the Ferrel cell in particular. Except, this needs to be deflected right because of the Coriolis effect, or force. Should be force, I'm going to call it effect because that's what most people use. So instead, these winds are deflected to the right, and we get our westerlies. Pretty cool. But now, let's use a real example, right? So, let's imagine we have high pressure up to our north, and low pressure to our south. Oh, sorry, my bad. Let's actually flip these. Give me a second. So we have 990 millibars, 1,000, and 1,010. This is high pressure now, and this is low pressure. So let's walk through a pulsar layer. The Coriolis effect will be red, and the pressure gradient pressure force gradient, which just states, high pressure wants to go to low pressure, will be in blue. As the two forces we are focusing on that are acting upon our air pulsar, which we will start right down here. To start out, the pulsar accelerates by the pressure force gradient to the north. All right. However, as it starts accelerating, the Coriolis effect accelerates a little bit to the, in this case, west. We're imagining this is in the northern hemisphere and the mid-lats. So the actual path veers just a little bit. Well, now it's moving faster, right? The earlier one was accelerating. It still is accelerating. And the pressure gradient force still wants to go straight north. However, the Coriolis effect, now that it's moving faster, because the Coriolis effect is based on a pulsar speed, that is important, in part, space is one of the things too, but, right? So it's now acting more. So now it's deflected even more to the right. And at this point, right, from this pulsar's vector, light is not, it's not this way. Light is instead down. And the PGF, of course, is still just pointing toward the low pressure. So at this point, and at the end, our pulsar will have the Coriolis effect counterbalance the pressure force gradient. And it'll be moving parallel to isoballs. We've seen this flow before, right? For example, at the beginning of our storm, or I guess before our storm even gets there, we have a high pressure to the north and generally low pressure right to the south. And we see isoballs that are like this, and we see our winds flowing straight west. And it helps usher in the cold air and helps give us our snow, right? But once again, you're probably looking at this like, where's the cyclonic flow? Well, we needed to go over that, because now we can actually go over cyclonic and anticyclonic flow. Right? Let's erase this all. So now that you understand geostrophic winds, we now have to understand what happens if isoballs are curved. Because they often are, right? So a low pressure with curved isoballs around it. And now we're going to do the same thing with pulsar veil. Right? The pressure force gradient wants to accelerate. We'll just imagine the pulsar is right here. That way it is accelerating straight inwards to the low. Straight inwards to the low. Right? The Coriolis effect wants it to accelerate the other way. Right? Wants it to deflect to the right in the northern hemisphere. Very important. Got a whole thing on my got a whole section on the test that was this in the southern hemisphere. Aced it, by the way, but I need another color. Green. Green's a great color. You also have the centrifugal effect. I'm not going into this, but just know it is basically going the opposite of the pressure force gradient. And remember, wind speed in our previous example was based on the pressure force gradient and the Coriolis effect. Them combined is what gave it its speed as it accelerated as it veered to the right. However, in this instance, notice how the pressure force gradient is being counterbalanced by both the centrifugal effect and the Coriolis effect. What this means is this pulsar is not as fast as geostrophic winds. This is sub-geostrophic flow. This is extremely important to know. Around low pressure, we have sub-geostrophic flow. That means winds are moving slower in the flow. Right? Yes. And that's just because the Coriolis effect is weaker because it's also being helped out by the centrifugal effect. So it's balancing the pressure gradient force. She also switches it back and forth, by the way, between pressure gradient and pressure force gradient. Doesn't really matter. Just know that this is subgeostrophic, right? Cyclonic flow is subgeostrophic. Now let's try anti-cyclonic flow, right? So, same setup, except there's a high in the middle. Here's our pulsar. Right? Have the pressure gradient force, but now it's acting to get away from the center. Right? And the Coriolis effect, let me make sure I got this right. And this also is complicated, so just bear with me, right? This pulsar is moving counterclockwise, right? This pulsar is moving clockwise, so it's moving at this point and wants to move down to the south. Remember, the Coriolis effect acts on the way the pulsar is moving. So if it's moving to the south, its relative right position is actually my left. So the Coriolis effect is moving that way. And the centrifugal effect, right, in this instance, it is with the pressure gradient force. Now this means the Coriolis effect is being counterbalanced by both the pressure gradient force and the centrifugal effect. And remember, the Coriolis effect is responsible for increasing wind speeds. That means the Coriolis effect here is relatively stronger than it is here and in geostrophic flow when isobars are parallel. So as such, anticyclonic is super, so above geostrophic wind speed. It's very important. So now, let's put this together. We put this together, and we can now start seeing how jet streaks work. So imagine this is an upper level map. And this is a ridge in the flow. This is a trough. This is a ridge, right? So low, high, high. And we have supergeostrophic flow around the high, right? And then we have subgeostrophic around the low, super around this high. So where does the wind accelerate and decelerate? Well, the wind has to decelerate here. So there's convergence, right? But remember, this is all upper level winds. Surface winds are a whole different thing that I don't think I will be explaining. So we have to decelerate in this part. But then as we go from so weaker wind flow, to faster wind flow, we have to accelerate. Well, would you look at that? It's right on the edge between our low and our high pressure. It's displaced in the northern hemisphere westerlies to the east of the flow. And this is divergence aloft. What does that mean? It induces surface cyclogenesis, right? Because divergence aloft means that the air is going out of the surface faster than the surface winds. As such, to supply the upper levels with this air, lift has to occur. So you get surface, low pressure. And that is how cyclonic flow works and why it is important. All right, now let's go on to some of the more fun stuff. Oh, I have chalk all over my pants. Cyclonic formation. And we are going to be using the polar front model because it's what I learned. This only deals with the surface, right? We will tie that in this stuff we just learned when we talk about lift, Fgen, and vorticity. Also, I guess I already talked about upper level winds. So, oh well. We will be cutting that section as I talked about with cyclonic flow. So, let me just make sure I get my polar front model all sorted out. So the polar front model says that cyclogenesis occurs between a continental polar high, and this is part 1, so we'll just say A. So you have this polar continental high to the north, and you have a subtropical or tropical oceanic moist high to the south. Consequently, you get a stationary front between the two. Of course, I could draw it out, but just know it's a stationary front. In some specific conditions, this surface front breaks. Now, if you were paying attention, you can probably guess under what upper level conditions this front will start to break. Hint, it's east of a upper level low because of the divergence aloft and some other factors that we will go into. So, step B. The front breaks, and this stationary front between the high and the other high turns into a bit of a surface low between them as the front breaks, and we get a cold front behind it, a warm front in front of it, due to surfaced winds blowing around it. Right? C. This is known as the frontal wave step. By C, we get the open wave problem. I don't know why they call it that. I think that's just how the theory works, because it's a closed, like they're all isobars closed. But at this point, our low pressure has become stronger. The initial highs that started this on the surface are sort of irrelevant. I won't be drawing them after this step. And at this point, we have a strong surface low with cold front, and also precipitation will be in green. And at this point, we have strong precipitation along the warm front and running back along the south. So you get this typical view of a front. Like, D is where we get our mature cyclone. It is also where we get our initial occlusion. For those who don't know, occlusion is when the cold front catches up to the warm front. So as you can see, there's the space that would be an occluded front, and surface low pressures are driven by temperature differences at the surface as they sort of feed into this feedback loop. that we will go over a bit more with vorticity, lift, and FGen. But for now, you need to know that this is the peak of the cyclone, as after this, the air all around the central low pressure is all of the same type. And during this part, we have a very strong moisture field, right? We have on the warm front, bit of moisture to the north associated with warm air advection, calm ahead, and then a line of showers associated with the cold front. Classic, right? This is your classic storm. You have warm air with the warm front, all that stuff. Then you have an advanced occlusion. This is step E, and after this, it dissipates, so I won't draw the next one. Right? And at this point, it's pretty much all cut off from this warm, moist air that was helping to fuel it. So while there's still some precipitation associated with it, it's not really strengthening. It's just sort of like still existing, and it eventually dissipates fully. All right, so that is cyclone formation. So the real thing is what forms this what forms step B where the wave breaks? Well, let's go over it. And this starts to put together everything we've learned. So you're now going to imagine we're looking at a 500 millibar map. And we're looking at a height map. So what we need to see is baroclinic, right? That's because baroclinic is when we have a short wave. So H5 looking like this, right? And it's compressing the flow out ahead of it a little bit. And what this means is the winds are flowing counterclockwise, right? And that means, so here's like an isotherm. Because isotherms generally follow height, as we discussed way back in part 1. But since we have a low pressure and we have winds, we have warm air and cold air advection. Out in front, because winds are blowing from the south, and the south is typically warmer, we have winds blowing across, right? This is important, this is very important. We have winds blowing across these isotherms and bringing in warmer air. So we have warm air advection. Same thing happens on the backside, right? Except it's cold air advection. Right? And if this is going on in wherever you have a cyclone, so this can be H5 if we have an H5 closed low. If we have an 850 closed low, this is happening. If we have a surface closed low, winds get tricky there because it's surface, you have friction, and it's not really, winds spiral in more because friction counterbalances forces. But generally, if you're above like 900 millibars, this is what you're looking at. Right, so when you have a really intense short wave and the atmosphere is baroclinic, which means that short waves are blowing across isotherms, you get this warm air advection, cold air advection. Right? And if you translated this to the surface, right, so this is, say, the H5, and this is, let's say 900 millibars, because it's not quite the surface, so I don't need to deal with that complexity. Well, you're going to have your surface low pressure displaced out here, right? You have it displaced to the east, where the warm air advection is, because warm air advection helps to generate lift. Cold air advection does the opposite. That's because warm air rises, so if you're bringing warm air at the same height level, it will rise comparatively. And also, if you remember all super and subgeostrophic flow, if you have a high and you have an upper level low, this is the jet stream. you're going to have convergence aloft here, divergence here, so you also have divergence, which further strengthens this surface flow. So what happens with that? Well, you have divergence aloft, you have warm air advection aloft, you get this powerful surface flow, and it follows along with this up as this upper stuff moves, the surface flow moves with it, and we go through the polar front model that we just went through. And yeah, and that's how you get storms. Going into lift and Fgen a little bit, right? Lift is influenced by warm air advection and divergence aloft, as I mentioned. And it is also because winds are blowing across isotherms and baroclinicity. Now, Fgen just means that you're tightening the baroclinic boundary. So if these are isotherms, positive Fgen would look like, see how close together they are? That means it's easier for winds to advect across them, right? It's a steeper gradient, which means there's more potential energy. And favors intense bands of precipitation underneath them because it's inducing lift into the atmosphere because of all this stuff we talked about. And the placement of these are mesoscale features, but they are driven by the synoptic scale stuff, right? That shows where the wind will be blowing north out ahead of the cyclone, which sets up where the isotherms are going to compress, which is Fgen, which sets up lift, and all of this other stuff. And yeah, oh, vorticity. Vorticity is the last thing I really got to mention. Like, to measure divergence aloft, there's no way to do that, as in like to do it cleanly. So instead of measuring divergence, we measure vorticity. And vorticity is the measure of the spin of small air parcels. Positive vorticity is counterclockwise. Negative vorticity is clockwise. And divergence aloft causes an increase in positive vorticity because of the spin. I don't fully understand the mechanisms behind vorticity, but basically it's measuring divergence aloft, which is linked to all this stuff, which is linked to precipitation at the surface. That's everything. Let me know what you guys think. If you want, I can do a video with a small board in a room that has one where I go over this setup and I go over all of these things working in tandem instead of just a theoretical space. And yeah, I hope you learned something.